Okay, so homework number 9, the last homework is due today. Monday next week, we'll have a review of chapters 10, 11, and 13, and the exam will be on chapters 10, 11, and 13 will be Wednesday next week. The exam's written, 10 problems, much like previous exams. If you're missing any labs, you can make up a lab after class, during the lab period today, or you can come in Monday or Wednesday next week, anytime between about 10 to 2. I'll be here. So we finished up chapter 13 on Monday. So I want to do a bit on gravity on chapter 12, just to finish off. So gravity, this is an example of something caused by gravity, as in a crater. So we'll start by talking about Newton's law of universal gravitation and the gravitational attraction of spherical bodies, and Kepler's laws of orbital motion, gravitational potential energy, conservation of energy for gravity, and tides. And I'm probably just going to skip over I'll skip through the problems. So Newton's law of universal gravitation was that Newton was able to make the insight that, the force accelerating an object downwards here on Earth is the same force that keeps the moon in its orbit, causes the orbits of the planets. Hence, universal gravitation. And the formula for that force the force of gravity is big G times mass 1 times mass 2 over the distance between the objects squared. And big G is the universal gravitational constant, which is 6.67 times 10 to the minus 11 meters squared per kilogram squared. The gravitational force is always attractive. It points along the line connecting the two masses. And so gravitational force between any two objects will form an action-reaction pair, as shown here. So the two forces form an action-reaction pair. And Newton's third law still is kept. Now, G is a very small number. This is because gravity is the weakest of the 4 fundamental forces. So gravitational force is negligible unless there's a very large mass involved. On Earth, that means the Earth is the very large mass in question. The gravitational attraction between objects around is tiny. So if an object is being acted on by several different gravitational forces, the net force on it is the vector sum of the individual forces. This is called the principle of superposition. So you can have a situation where the gravity between multiple forces is balanced. So if you're in between two equally massive objects and you're in the middle, the gravity pull from each of them will cancel each other. And you can find points in the orbits of like planets and the Earth where that balance occurs. These are called the Lagrange points. You may have heard of them. So these are places where gravity between the Earth, the Sun, and the centrifugal force of the orbits balance out, and you have these stable-ish points. So, for example, the James Webb Space Telescope is at Earth's Lagrange 2 point, far away from here. So if you have two apples of mass 0.11 kilogram and mass 0.22 kilograms sitting on a dining room table, and you want to figure out the force of gravity between them when their separation is 13.2 centimeters or 132 centimeters. So G is 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. Mass 1 is 0.11 kilograms. Mass 2 is 0.22 kilograms. Our initial radius is 0.132 meters. Our second radius is 1.32 meters. We're looking for the force. Force is big G times mass 1 times mass 2 over radius squared. So when they're 0.13 meters apart, 6.67 times 10 to the minus 11 times 0.11 times 0.22 over 0.132 meters. The force of gravity is 9.26 times 10 to the minus 11 newtons. You compare that to the weight of these objects. The lighter apple has a weight of about 1 newton. So we're talking about a difference of around 10 to the 10 in force. And here, if they're 1.32 meters apart, the force of gravity between them is 9.26 times 10 to the minus 13 newtons. We increase the distance by a factor of 10. That decreased the force by a factor of 100 because it's an inverse square law. And lots of forces are inverse squares. So them is similarly an inverse square. So if you have two charged particles, it will have the similar response. Now, gravitational force between a point mass and a sphere. For a sphere, it turns out if you have a symmetrical sphere, the force is the same as if all the mass was in the center of the sphere. Basically, if you have a ball, that if you rotate it, the mass distribution doesn't change. That will act as if all the mass is in the center of the object. Basically, all the forces from all the little bits add up to be as if all the force was in the center, all the mass was in the center. What is going on? Why is this not working? We run out of power. Oh, I think it's died. Well, so if we think about the gravitational force on objects of the Earth is basically a ball. So the center of the Earth is 1 Earth radius away. So the force on an object on the Earth is G times mass of the Earth over radius of the Earth squared, which becomes mass times big G times mass of the Earth over radius of the Earth squared. Mass times a constant. Well, that's familiar. That's what little g is. So and if you think about that, the acceleration of gravity will decrease steadily with altitude. As you go to higher and higher altitudes, the acceleration of gravity gets smaller and smaller. Which is why at the International Space Station, the acceleration of gravity is about 8 and a bit. Instead of 9.8, nearly 10. And once the altitude becomes comparable to the radius of the Earth, the decrease of the acceleration of gravity is a lot more. So out by the orbit of the geosynchronous satellites, the acceleration of gravity is a fraction of a meter per second squared. Now, how we initially, this fact that spheres act like their point masses is how the actual, big G was initially measured by Cavendish. You had a couple of large spheres set up like this. So they were bigger than this picture things with like a thread, well, it was a wire and a mirror. And he measured the force of twisting with these spheres as you move the outer spheres. And thus was able to measure the gravitational constant. It's a tiny twist. Even though the gravitational force is small, the mirror allows the measurement of tiny deflections. And measuring big G also allowed the mass of the Earth to be calculated because you can use the local acceleration of gravity and the radius of the Earth. Those were both known to figure out the mass of the Earth if you know big G. I'm just gonna, you could find, here's an example of finding the acceleration due to gravity on the surface of the moon. The G on the moon is G times the mass of the moon over the mass, the radius of the moon squared, which gives you 1.62 meters per second squared, which is about a sixth of G on Earth. And if you want to find the weight of the rover that had a mass of 225 kilograms on the moon, you just multiply by G of the moon, and you'll get a weight of 365 newtons. And the weight on Earth would be about 6 times that, 2,210 newtons. Now, when you can get a steady state traveling around an object, if you're traveling sideways fast enough, basically you can fall towards the ground and constantly miss. And that leads to an orbit. So Johannes Kepler made detailed studies of the apparent motions of planets over many years and was able to formulate 3 laws, which you can derive from Newton's laws of motion and Newton's laws of universal gravitation, but Kepler was well before Newton. Planets follow elliptical orbits with the sun at one focus of the ellipse. As a planet moves in its orbit, it sweeps out an equal amount of area in an equal amount of time, which means the closer it is to the sun, the faster it moves. Closest point is called perihelion. The furthest point is called aphelion. Amusingly, the Earth is closest to the sun in January. The Earth's orbit is basically circular. It does not really affect the seasons. The Earth's orbit is slightly elliptical. In fact, the Earth is closer to the sun during the northern hemisphere's winter than the summer. Is the orbital speed of the Earth during the winter greater than, less than, or equal to its orbital speed in the summer? And which of the following is the best explanation? The Earth sweeps out equal areas in equal times, and hence it moves faster in the winter when the distance from the sun is smaller, is the correct answer. And the period that of a planet, the time it takes to orbit once, its year, increases as its mean distance from the sun. R is raised to the 3/2 power. And this can be shown as a consequence of the inverse square form of the gravitational force. And so a geosynchronous satellite is one whose orbital period is equal to 1 day. If you have a satellite orbiting above the equator, it'll be in a fixed position with respect to the ground. And these satellites are used for communications and weather forecasting. And there's only a limited number of places we can put satellites up in geosynchronous orbit before it gets full. So GPS satellites, on the other hand, are not in geosynchronous orbit. Their orbit period is 12 hours. And triangulation of signals from several satellites allows for a precise location of objects on Earth. But they have to know where they are at all times. And then, yeah. And Kepler's laws also give us insight into possible orbital maneuvers, where you can go from one orbit to another, as shown here. So if you want to go from a bigger orbit to a smaller orbit, you fire your first retro thrust, and you go into an elliptical transfer orbit, and then a second one to get to your final circular orbit. Or you can do the opposite, fire your first accelerating thrust, and then a second one to get into a stable second circular orbit. So if the Earth revolves around the sun once a year at an average distance of 4.5 times 10 to the 11 meters, when the period of revolution for the planet Mercury, whose average distance from the sun is 5.97 times 10 to the 10 meters. Since the period is proportional to the radius to the 2/3, this is just a constant. The period of Mercury over the period of Earth is equal to the radius of Mercury over the radius of Earth to the 2/3. So the period of Mercury is 3.16 times 10 to the 7 seconds times the ratio of the distances to the 2/3, which comes out to 7.58 times 10 to the 6 seconds, or 0.24 years, or 87.7 days. Now, gravity also has a potential energy. On Earth, the changes in radius are so small, we approximate it with mgh. But in general, the gravitational potential energy can be found to be minus big G. The potential energy gravitational is minus big G mass of the object, mass of the large object it's orbiting about, over radius. And 0 is at the point at infinity. Just a reminder. So very close to the Earth's surface, the gravitational potential energy increases linearly with altitude, because the radius changes so little that 1/r, it's approximately linear. So delta U equals mgh. Gravitational potential energy, just like all other forms of energy, is a scalar. It therefore has no components, just a sign. And it's usually negative just because we put the point at infinity equal to 0, because it makes the math easier. And you could get this by taking the integral of the force. That's how you get it. So if we use U equals G, this formula to find the gravitational potential energy of a 976 kilogram meteorite, but it's 10 Earth radii from the center of the Earth and on the surface of the Earth. I'm just going to do this. So if we plug that in at 10 Earth radii, it's negative 6.1 times 10 to the minus 9 joules. And on the surface of the Earth, it's negative 6.1 times 10 to the 10 joules. 10 times as much. Now, when something's in an orbit, total mechanical energy of an object of mass m at distance r from the center of the Earth is conserved. This confirms what we already know, that as an object approaches the Earth, it moves faster and faster. And as an object orbits, it's, when it's closer to the Earth, it's faster. When it's further from the Earth, it's slower. So here's sort of the potential energy, kinetic energy relationship. Because remember here, potential energy is negative, so the energy is positive and of the same size to add up to 0. Another way is you can visualize it as a well falling down, and things would sort of roll down into the well kind of idea. Now, the escape velocity or escape speed is the initial upward speed a projectile has to have in order to escape from something's gravity. The escape velocity, it's just enough kinetic energy to equal the potential energy. So the escape velocity ends up being square root of 2g times mass of the big object over the radius you are from it. So the escape velocity for Earth is square root of 2g mass of the Earth over radius of the Earth, which is 11,200 meters per second, or about 25,000 miles per hour. And here is the speed of a projectile as it leaves the Earth for various launch speeds. At 0.75, you see it comes to a stop. It makes it up to this many radii. 0.95 makes it a little over 10 Earth radii. At the escape velocity, it will go on forever. And above the escape velocity, it will go on forever, but faster. And there's escape velocities for any object. So, we have sent a few things faster than the escape velocity for the sun at the Earth's orbit, and they have left the solar system, like the Voyager probes. And I think New Horizons will eventually do that. Now, if an object is sufficiently massive and sufficiently small, the escape velocity will equal or exceed the speed of light, and gravity will win, and nothing will be able to escape the surface. That's a black hole. And general relativity gets weird, and there's a mathematical singularity. Another interesting thing is that the implication that light gets bent by gravitational fields. And this can be seen when we do a distant galaxy beyond a close galaxy. This is called gravitational lensing, and many examples of it have been found. I think the first time gravitational lensing was observed was during a solar eclipse. A star behind the sun was lensed by the sun itself. So you could see it during that solar eclipse. And if you want to calculate the escape velocity for an object launched from the moon, you need to use the mass of the moon and the radius of the moon. So the escape velocity is 2 times g times the mass of the object over the radius. So 2g mass of the moon over the radius of the moon. You plug in the numbers, you get an escape velocity of around 2,370 meters per second, or 5,300 miles per hour. And is the escape velocity for a 10,000 kilogram rocket faster, greater than, less than, or equal to the escape velocity for a 1,000 kilogram rocket? And the answer is that they are the same, because it only depends on the mass of the Earth, not on the mass of the rocket. Now, usually we can treat planets, moons, and stars as though they were point objects, but in fact, they are not point objects. Things have extent. When two large objects exert gravitational forces on each other, the forces on the near side is larger than the force on the far side, because the near side is closer to the other object. And that difference in gravitational force across an object due to its size is called a tidal force. And that is because that difference in gravitational force from the moon is what causes tides on Earth. As Earth rotates relative to the position of the moon, water sloshes about because of that difference in gravitational force. There are bulges on either side of the Earth. So this is a general tidal force on the left and the result of the lunar tidal forces on Earth on the right. And that's why there are 2 high tides and 2 low tides each day. And tidal forces distort the shape of objects orbiting around other objects. In extreme cases, like near black holes or neutron stars, tidal forces can tear things apart. But they also heat up the interiors of the Jovian moons and things like that. And they also can affect the way things rotate. So tidal forces can result in what's called orbital locking. So this has happened with the moon. The same side of the moon always faces towards the Earth. And the moon is slowing down the Earth's rotation. So if uninterrupted, the Earth would eventually slow down, so the same side of the Earth always faces the moon. And if a moon gets too close to a large planet, the tidal forces can be strong enough to tear the moon apart. This occurs within what is known as the Roche limit. Closer to the planet, you have rings, not moons, as can be seen for Saturn. And that was chapter 12. Very quickly. So I am going to stop there. If anybody needs to make up a lab today, they can do it today. Let me get back to the beginning. So So lab makeups, I'm gonna do lab makeups today, for anyone who wants to do it now. Or you can come in, and if you're missing any labs, you can just check on Blackboard. If you're missing a grade on any lab, you need to make it up. I'm happy to check right now. If you are missing any labs, you can do it either today, right now, or you can do it on Monday and Wednesday next week. Anytime from around 10 to 2, I'll be around. So I'm going to stop sharing and I'm going to end the meeting.